Hello, my name's Julian Edgar and I'm the author of this book, Designing and Building a New Energy Efficient Home. What I want to cover in today's video is why ventilation is really important in a passive solar home. There are 3 reasons. Let's take a look. So you want to build a new energy efficient and comfortable, healthy home in southern Australia. So ventilation is one of those key aspects to get right. There's a lot more to it than it first appears. It's easy to go, well, of course you need ventilation, but why do you need it and how do you achieve it? So ventilation is important for 3 reasons. The first one is to provide good quality air for the occupants to breathe. The second one is, in summer, to cool you by moving airflow. And the third one, also in summer, is to remove heat that has been stored in the thermal mass. Now you can see those 3 reasons are all quite different. They're tackled in different ways. There are different ideas that need to be brought to bear when you're looking at each of those 3. So the first one was good quality air to breathe. Now, air quality can be assessed on a whole bunch of metrics, but a really good proxy for air quality is CO2 levels, carbon dioxide levels. When we breathe, when we exhale, we're breathing out CO2. And so if CO2 levels are high, it's indicative of insufficient airflow. Okay, so it's a really good proxy. You can also look at things like VOX, volatile organic compounds. You can look at formaldehyde. You can look at dust levels, but CO2 is a really good proxy of those. Now, CO2 should be kept below about 1,000 parts per million. The atmospheric level of CO2 is about 400 parts per million. So we can see that even at 1,000, we've doubled the CO2 level over atmosphere that's inside our homes. Now, I've picked 1,000 because that's on all the literature perfectly safe. In fact, you can go well above 1,000 and not, die, but 1,000 constantly or below is perfectly safe. So what's the level inside your home now, and what would be the level inside a new passive solar home? Well, the good news is that CO2 levels below 1,000 are easily achieved with normal levels of ceiling. When I say ceiling, I mean not the ceiling above you, but the ceiling all around you, the ceiling of the house. Normal levels of ceiling, as opposed to hermetically trying to seal yourself into the house, which I don't think is necessary. Normal levels of ceiling gives you perfectly adequate air quality because air infiltrates through tiny gaps in the fabric of the house. If you go and look at your back door right now, you'll probably see, if you look really closely, a gap around it. Even if you've put rubber seals, there'll still be little gaps and the air moves in and out through those little gaps. Now, a lot of people will say, oh no, air quality in normal houses is terrible. But they've typically never actually measured them. They're just going on what other people have told them. So here on this graph, I have a indication of air quality in our passive solar home. 1,000 is at the top of the graph. 400, which remember is outside air quality, is at the bottom of the graph. And you can see over these about 5-6 days, the absolute maximum peak was 600. Now, I've seen higher levels than that in our passive solar home. I've seen 850, which is up here, but you can see they're always well below 1,000. Now, that's because the house is not sealed airtight. The house has got little imperfections that let air move through, and I'm very comfortable with that. It means we are always going to be getting sufficient air to give us good air quality, even if the power goes off. And so, for example, if you were relying on a mechanical ventilator, that would go off too. Here, the house naturally provides sufficient air for good breathing quality. Now, if you're worried about air quality, by all means, get a monitor. This particular monitor here measures CO2 only. You can get little monitors like this that also measure VOX and formaldehydes and PM2.5 and so on. But as I said earlier, most people who say, oh, air quality in homes is dreadful, have never actually measured it. When I talk about air quality in a home, there is one area to be really aware of. And that is, if you sleep in a bedroom at night and you shut the door, you are exhaling all night. And I have seen in that situation in homes, the air quality worsen considerably. The CO2 really rises, especially if that door closes tightly, there's no gap at the bottom. So if you're using a CO2 monitor such as this, don't just leave it in the middle of the house and say, well, that's the air quality. Actually move it, especially to rooms where the doors are closed. Now, if the CO2 level goes up in that closed off room, you've got to change something. You've got to leave the door ajar at night, or you've got to have a window slightly ajar or something of that sort. So I'm not dismissing the notion that air quality, can be ignored. Air quality certainly needs to be looked at. But typically in a normally sealed home, the air quality is absolutely fine. It's those closed bedrooms at night where you've really got to be careful to actually check. So the first use of ventilation, the first requirement of ventilation, is it provides you with sufficient air quality to allow you to breathe. The second reason why ventilation is really important is moving air can cool you. Now, in many, many climates, there's a cool change that occurs in the late afternoon. If it's a coastal environment, it might be a sea breeze picks up, wind moving from across the ocean, which is typically cooler than the land, and so bringing cool air towards you. In inland environments, it can be gully breezes, katabatic breezes, where the cool air slides down the valley and past you. If you live in an environment where in summer there are cool changes, you want to be able to bring that cool air into your house and cool you. Cool you because it is moving, and moving air better cools people than stationary air. It helps evaporates the sweat on your body, and also the air going past your skin where your vasodilation has occurred, and so your skin is warm. Moving air will better cool that because the cool air is replacing the air that you have warmed by being in proximity to you. So moving air can cool you. Often we use a fan to do that, but it can also be air from outside. Now, you might be saying, well, so what? Well, you've got to have sufficient openings to allow the air to flow through your house. And air movement through a house occurs because of different pressures. A high pressure at one location, a lower pressure at another location, the air will flow between. And so when you're designing a passive solar home, you've got to be really careful that there will be sufficient ventilation openings that develop high and low pressures for air to move through. And there are plenty of references, including mine, which cover the way air moves through homes. These diagrams give you a bit of a feel for what I'm talking about. If you look up this top one, you can see a plus. That's where high pressure is being developed by the outside wind, and therefore the air blows into the house there. And because this is in the lee of that wall, a low pressure, a negative pressure develops there, and so the air flows through. And you can see all of these different diagrams show different ways in which high and low pressures are going to be developed. Although here you can see high and high, so no airflow occurs through the house. So designing a house so it can be thrown open when there is a cool change and the air can blow through the house is really, really important part of a passive solar home design. Excuse me. The third reason that we want to be able to have good quality ventilation in a passive solar home is so we can remove any heat that has been stored within the home. Now, I'll cover this in a lot more detail in another video, but the way a passive solar home keeps cool in summer is you shut the house up, and inside the house there are materials that can absorb heat. Those materials are called thermal mass. A typical example of thermal mass is a concrete slab floor. So on a hot summer's day, the temperature of the thermal mass gradually rises because it is drawing heat from the air in the house. So the air in the house stays cool and the thermal mass gradually rises in temperature, but it's still lower than the air temperature. So you're storing heat in the thermal mass. Now you've got to get rid of that heat. It can't just be stored forever. And the way you get rid of that heat is you open the house that night when it is cooler. You then have the air flow through the house, removing the heat that has been stored in the thermal mass. So in a passive solar home, in a climate that has hot days and cool nights, what's called a high diurnal range, this is a vital way of keeping the house cool, and you must have airflow through the house at night to get rid of that heat. I'll give you an example. So here is some data logging from my house, our solar house, from last summer. Outside, you can see the temperature was 39.5 degrees, very, very hot. Inside, common means it's the middle of the house, inside the air temperature was only 24.5. Now the main reason it was so much cooler inside the house, and I'll tell you when you walk in from 40 to 24.5 it feels very cool, the main reason is because the thermal mass was absorbing the heat from the air inside the house. How hot was the thermal mass? Well, here is a measurement of the temperature of the slab, the concrete slab. It was 21.7. You might say, well, that seems pretty cool, but it probably started at about 20.5 on that day. So it's risen about 1 degree Celsius during the course of the day. And the reason it's risen is it's absorbing all that heat from the air. Because the thermal mass has got so much capacity to absorb heat, even a tiny temperature increase of the thermal mass shows it's absorbing a lot of heat from outside. So if the temperature of that next night was less than 21.7, we throw open the house, the air flows through the house, and it cools that thermal mass, the concrete slab that's absorbed that heat. Now this is an extraordinary effective way of cooling houses, so long as the night temperature drops sufficient to be able to remove the heat that night. I will talk a lot more about thermal mass in a video that's coming up, but it's a really, really key part of the way in which a passive solar home operates. Now, we talked about throwing windows open for ventilation, as in a cool breeze or something like that. But when we're cooling the thermal mass, especially if it's a concrete slab, that air from outside has to flow across the floor, has to flow across the thermal mass, so wet the thermal mass if you like. Now that means a window that's 2 meters above the ground and you open, it's not going to cool the thermal mass very well. So to cool thermal mass, if it's the concrete slab floor, which is a common example, you really need sliding doors or something like that that opens, and so the air comes in and flows across the floor. So you can see there are some subtleties here that, just a glance at the title of this video wouldn't have shown you. Oh yeah, ventilation, that's all pretty obvious. Well no, there are actually some things to really keep in mind. So here's an example of thermal mass in operation taken from a textbook. Top diagram, warm daytime wind, closed windows, light colours, and here inside the enclosure is the thermal mass. The dotted lines here show concrete on the inside, and you can see the fans on, which circulates the air around, keeping you cooler, and you can see the person is radiating their heat. Their heat is going into the thermal mass. So the thermal mass is getting hotter, it's warming. And then that night, here's the moon, that night everything's open, and so the air can flow right through and cool that thermal mass. So it's all in the textbooks, and does it work? It works absolutely superbly. So we've got ventilation, air movement in and out of the house by these means. Infiltration, which is occurring naturally all the time. Open windows, for when, for example, you want to have a sea breeze come in or a gully breeze come in. Open doors, especially when you want to cool thermal mass, because then the air will flow across the floor as well as higher up. And I've added another one here because I want to use it as a quick example, and that's convectional ventilation. Now, in convectional ventilation, air is rising, hot air is rising. we make an opening that lets that hot air out, and that will help draw cool air in. We talked about pressures, moving air. If air is flowing out of an enclosure, like a house, it'll lower the pressure inside that enclosure, and that will draw air in. Air will be pushed in from outside. Convectional ventilation is very, very powerful because it'll work even when there's no wind. Now, look how open doors and open windows is reliant on wind to provide the pressure to move the air, but convectional ventilation will work even when there's no wind, when it's dead calm. In our house, our passive solar home, we use a convectional ventilation system. It comprises a big ventilator, rotating ventilator on the roof. That's 600 millimeters throat diameter, and not only does the wind spin that ventilator, it's also got an electric motor in it. So when it is dead calm, I can operate the electric motor. It's got a speed control. I just flick the switch on the wall, decide how fast I want it to rotate just by turning a knob. So that draws air out of the roof space. And the rest of the roof space is reasonably well sealed. It's sealed around the edges, for example. It's sealed at the crest of the roof, at the ridge. So it lowers the pressure in the roof space. Connecting the house, the interior of the house to the roof space, are vents like this. Now this one is in a wall at the top of a arched room, a room with a arched ceiling. Behind this vent is a door, is an insulated door which opens when I flick a switch. So normally that vent, and the ones are also in the ceiling in the normal parts of the house where there are flat ceilings, they are sealed by this insulated door which shuts them off. When I want air to be able to flow through, I flick a wall switch and it opens the door, allowing air to flow through into the roof space. Now remember, air has been drawn out of the roof space by this ventilator over here. And so if I open a hatch, which is what I call those vents, and I open a window, air will flow in through the window, across the house, inside the house, up through the vent, into the roof space, and then out through that ventilator. And you can actually see the air doing that. Here I am in the roof space, and I'm holding a little velometer, which is a little flow meter, and you can see 150 feet per minute, it's an imperial meter, 150 feet per minute flow through the open hatch that's going out through the ventilator. So what we do is, if we want to cool the thermal mass at night and it's dead calm, I'll power up the ventilator, I'll flick the switches to open the hatches. There are 4 hatches through the house, and I'll make sure a door or multiple doors are open, and then the air flows through all night, even if it's dead calm, and that cools the thermal mass. And when you're lying in bed, incidentally, it just gives you just a perceptible feeling of airflow over you. We do this when we're trying to cool the thermal mass on summer nights, and so that airflow actually feels really, really nice. The bedrooms also have ceiling fans. We so far don't even have to use those ceiling fans because there's just this imperceptible breeze, or it's perceptible, but it's very, very small, very tiny breeze across you. Now, convectional ventilation, as I've been saying, has advantages over just using wind to move air through the house, but you don't have to use it. If it's a windy night, I don't open the hatches, I don't power up the ventilator. The air just flows through the house normally, from open doors through to open windows and so on. But it's a very, very important idea, I think, to keep in mind. So good passive solar design comprises orientation. If you haven't seen the video on that, go and have a look at it. That's the direction most window area in the house faces. It comprises shading, how you let winter sunshine come in those windows, but stop summer sun coming in. It comprises ventilation, that we've been talking about in this video. It comprises thermal mass, which I mentioned in passing, but which I'll cover, I think, in 2 videos. It's such an important area. And it comprises house layout. Now, I've said these don't need to cost anything. You might say, hey, hold on, what about your convectional ventilation system? Yeah, that cost a small amount. The powered ventilator cost, I built those opening hatches, but they could have been built by anyone. They're very, very simple. The switches on the wall, a bit of wiring, it was an absolutely trivial cost in terms of the whole house cost. And of course, you can achieve ventilation without that anyway, just by opening windows and doors. It can be free. So good passive solar design is about fundamentals. It's about getting the fundamentals of the house right, not just putting on technological band-aids, not just saying, oh, we need to double the insulation because otherwise the house will get too cold or too hot. Not just saying, oh, we need special windows that we'll import from overseas because that's the only way we can meet energy ratings. None of those things are needed. Insulation is just standard insulation that's required by 7-star design in Australia. The windows are just off-the-shelf double glazed from my local supplier. They're not anything absolutely fancy and special. We're just talking about getting the fundamentals of the house right, and then of course it performs perfectly well in the climate. The book's called Designing and Building a New Energy Efficient Home. It's not out yet. It'll be out mid or maybe mid-late 2026. The book's written 90%, but I'm waiting until I have log data on everything for that house for a year. So that will include CO2 levels, that will include interior temperatures. I even measure the volume of air going through that rooftop ventilator so we can see how much naturally goes through and how much goes through when I flick the switch. The book's called Designing and Building a New Energy Efficient Home. Thank you.